So in the previous part, we discussed if we take an arbitrary extensive quantity B uppercase, what is the flow rate of B across the control surface that makes up a volume. That is, if you take a volume, it has got to have a bounding surface. That's what we call as control surface, and that would be the integral of the density times the corresponding intensive quantity, where lowercase b is B over the mass of the system, lowercase b times V dot n. V dot n dA, as we saw in the previous video, is the flow rate, is the volume flow rate across a surface, and we multiply that by density to get the mass flow rate, and B is the quantity per unit mass, so multiplying with B gets you uppercase B. So this is the flow rate of B across the control surfaces. You integrate over the area. Okay. I'll write a double integral here to show that it's an integral over an area. Similarly, if we think of the rate of change of B within the control volume, that is what happens in this volume, whatever is happening in this volume that's changing B, the rate at which B changes is the integral of rho times B. Okay, I'm sorry, B times, rho dV, that is the mass contained in the volume, and when you multiply that by B, you get the quantity uppercase B, and you sum over the entire volume. So you evaluate a triple integral over the entire control volume, and the rate at which this changes, which is the time derivative of this quantity, is the rate of change of B within the control volume. So we put together these pieces in the previous video, and now we want to make a statement of logic. There is a very long detailed derivation in the book on this, but ultimately it boils down to this equation here called Reynolds transport theorem, and we just want to see this without the derivation. We just want to do it intuitively. So if you consider a quantity B, it is going to change. That is, if you take the value of B at a particular location, at this point, let's say, what is the total rate of change of B considering two types of processes. One is B can be brought in and taken out. Like for example, if you had a fan here, if you had a fan that's blowing cold air, or hot air, that is, let's say you have a heat gun that is blowing hot air, the hot air along with its flow also brings the temperature or the thermal energy that is brought into this volume. So like for example, if you are thinking of people with them, when they migrate, they bring property, they bring their belongings, so they bring some money. So each person not only brings themselves, they also bring something else, and that something else is what we keep referring to as B. Now you could have a flow of B in and out across the surfaces, across the boundaries, or across the borders, and you could have creation and destruction of B within the control volume, of B within the control volume. Like for example, this could be the number of people born or dying inside a country. That would be the creation and destruction of B within the control volume. The statement of logic is the total rate of change of B is the rate of change of B within the control volume. This is a volume change plus the flow of B across the control surface. Okay, if you add these two, you should get the total rate of change. So I put this together, the total rate of change, I'll call this term 1, term 2 and term 3. What I am writing is 1 equals 2 plus 3. The total rate of change of B is equal to the volumetric rate of change plus the surface rate of change, or the flow across the surface. And this very important result is called Reynolds transport theorem, and we will apply it for mass conservation, momentum conservation, and you can also apply it for angular momentum, internal energy, which will be first law of thermodynamics. We did this in the Thermo 1 class last semester, and entropy, which is second law of thermodynamics. At least in this course, we will only focus on mass and momentum. We are going to see how to apply Reynolds transport theorem for a control volume that has both volumetric changes and surface changes. Okay, so this is a very important result in the whole of this course, where we try to get a relation between the flow of a quantity and the change of a quantity within a volume, and connect it to the total rate of change of a quantity at a particular point. Okay. Now moving on, we want to talk about how or what type of simplifications are possible when we try to use this Reynolds transport theorem. So once you have understood this flow across the surface and change within a volume, the next thing to do is start applying this theorem for different types of properties or different types of control volumes. So let's rewrite this. dB over dt is the time rate of change over the control volume rho b dV plus flow across the surface rho b v dot n dA. Now through the examples, we want to see how to evaluate v dot n, how to do this integration, how to choose the control volume to make your problem solving easier, and what is on the left side. Like still now we have been talking in the abstract about B being some mystery quantity, and now we want to give B two specific quantities. Let's say B is mass. The other choice is B is linear momentum. MB. Okay. The right side of this equation, the right side here, the right side is a balance statement. It doesn't tell you anything about the physics of the system. It simply says what changes within and what flows across must add up to the total rate of change. It's just a statement saying 1 plus 2 equals 3, or 2 plus 3 equals 1 in our notation there. This is for any quantity. That is, all it says is it should be equal to the rate of change of B. Okay. Now for example, if B is taken to be the mass, if you take the mass, if you take a volume that is a control volume, or I'll just use the picture that I have there. Okay, I'm going to write dB, mass of the system, divided by dt equals the rate of change of, what is B for mass? If B equals m, then lowercase b is B over m, or m over m, which is 1. Okay, so I have rho times 1 times dV. Density times 1 times dV plus dot n dA. Alright. Now if I take principle of conservation of mass, what do we know? If we take the principle of conservation of mass, mass is neither created nor destroyed. Mass is neither created nor destroyed. Okay, which means if you take the mass of a fluid system, if you take a designated amount of fluid, its mass should be a constant. If you take a designated amount of fluid, its mass is a constant, which obviously leads, if you take the derivative of mass with respect to time, the total rate of change with respect to time should be 0. So what we got for the right side from using the Reynolds transport theorem, the left side here, this is connected to physics. This has to come from a conservation principle. This has to come from a conservation principle that connects the rate of change of that quantity, in this case mass, to some physical reality. And that physical reality is mass is a constant. It has to be conserved. That's what classical physics assumes. Mass is conserved. So the rate of change of mass should be 0. So this statement here for mass conservation will become this statement will become 0 equals the derivative with respect to time over the control volume rho dV plus the integral with respect to the double integral over the area rho v dot n dA. Okay, this is mass balance for a finite control volume. This is mass balance for a finite control volume. It's one of the most important equations in this class, which we will use to solve problems. And there is some physics in here that we will discuss. Okay, so along with Reynolds transport theorem, the first application of this theorem gives us mass conservation or mass balance for a finite control volume, and that would be 0 equals the partial derivative over the volume rho dV plus over the area rho v dot n dA. Okay, we will do examples. We will do examples how to use this equation. But the mass conservation for a finite control volume is this statement. And you can choose the control volume whichever way you want, however big you want, however shape, whatever shape you want. That's up to you. That's where your intelligence comes in. You choose it such that the evaluation of these integrals becomes easier. Okay, we'll see that through examples. So we did this for mass balance. Okay, if through the same formulation, if we try to choose this B to be linear momentum, we choose B to be linear momentum, I'm going to say the lowercase b is simply velocity. Okay, and the rate of change of linear momentum, instead of mass, I'm going to say m system times the velocity, or I'll write linear momentum. Linear momentum. Okay, Now how is linear momentum connected to the physics? We need to find a physics principle or a conservation principle that tells you how linear momentum is related to some other physical quantity, which is the rate of change of momentum is equal to the sum of all external forces acting on the system. It should be equal to sum of all the external forces acting on the system. So that principle is basically dP over dt is sum of all the external forces. Okay. So here we are, dP over dt. On the right side, instead of 1, I should be having lowercase b, which is velocity. That is, previously here I had b to be 1 for mass conservation. Now b is equal to velocity for momentum conservation. So I am going to have rho v dv plus double integral over the control surface rho v dot n dA. Rho v dot n dA. Okay. Now let me erase this picture. If I piece this together, if I piece this statement and this statement together, I have sum of all external forces, which is the left side, should be equal to the rate of change of momentum in this volume plus the rate of flow of momentum across this volume. That is, this quantity rho times v dot n times dA is volume flow rate. Is mass flow rate. And then I write m and then I write v bar. So v bar times rho v dot n dA. This whole quantity is mass flow rate. Mass flow rate across the control surfaces. Across the control surface. When I multiply this by momentum per unit mass. This is momentum per unit mass multiplied by mass flow rate. What I get here is momentum flow rate. This quantity v times rho v dot n dA is momentum flow rate, just like rho v dot n dA is mass flow rate. Just like mass is a quantity that flows with the flow, you can also think of how much momentum is flowing, which is momentum flow rate v times rho v dot n dA. So this is mass balance for a finite control volume, and this is momentum balance for a finite control volume. This is momentum balance for a finite control volume. So let me try to make it easier for you to read. So here is the general principle. Here is the general principle. We start here, step 1, general principle, and then we get to mass conservation, step 2, and then we go to momentum conservation, step 3. This has already been written, so I can erase it. have here in the bottom, is that you go from the general idea, you tie it to the physics that describes the quantity B, the physics or conservation principle for the quantity B. It could be mass, B could be mass, or B could be momentum, and depending on that you get either mass conservation or momentum conservation. So the concepts that you have learnt is, here is mass flow rate, rho v dot m dA. It's still, I know it's still a bit hazy, but we'll see them through examples. And then momentum flow rate, which is P times rho v dot n dA. Okay? So we'll take a break here, and in the next part we'll try to add a few more remarks and wrap up this module.